Good morning, everybody. Welcome back. Tomorrow, no lab, right? Did everybody see the announcement? I'm going to be having what I like to call my Dr. Octopus surgery. In the movie Spider-Man 2, where Doc Ock has he has that spinal thing, and then they inject, right? All the thing. That's going to be me tomorrow, and they're going to do it one at a time, and I'm not going to have an exoskeleton when I'm done. So they just told me that they have to sedate me because I guess I'm too much of a problem. Although I asked too many questions during surgery, I think is what it is. Questions like, "Ooh, can I watch?" and "Ooh, what does that do?" And so the sedation is more the problem than the actual surgery is, right? So no work tomorrow. No, not allowed to drive. Not allowed to eat for most of the day. That kind of stuff. So, but I'll be back on Thursday, unless you guys arrange something with the doctors. But the test will go on without me, regardless. All right. I said the T word. When's your test? That is the correct answer. It's this, not this Thursday, but the Thursday after, right? So that means we have today, Thursday, Tuesday, right, to do chapter 8. And then we're reviewing Wednesday for your exam on Thursday, right? So, whoo! And I know nearly all of you are feeling like not only has the train left the station without you, but it has run you over in the process, right? Like you're not like, Mr. Bay, I'm not even keeping up. I'm bleeding on the tracks, right? And so for those of you who don't understand the analogy, right? Lots of people just through chapters 5 and 6 just feel like they don't know what they're doing. If that's you, good job. That's the way it is, right? The first time, the second time, the third time through this stuff, you're just like, what the heck is going on here? You hold on for the ride. You trust the process, the problem-solving process. You do your best, right? And you work hard. You work hard to sort these things out, and it'll be okay in the end. We've been doing conservation of energy, and so we need to talk about potential energy, and then we can put it all together and really start some problem solving. I've said this before. I really feel like chapter 7 and 8 should be the same chapter. It's kind of like 5 and 6 should be the same chapter. They're the same ideas. And so it's time to talk about gravitational potential energy. If I grab this ball and I let go, right, we know that it's going to fall because gravity, the Earth's going to pull on it. That's the gravitational force. But let's write down the work that gravity does. So what's work? Just real quick review. Yeah, it's a force times a distance, right? Come on, iPad, we can do it. Apparently we can't do it. Nope. Well, that was anticlimactic, wasn't it? You connected. Ha 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 ha. Ha ha ha. All right. So work, force times distance, right? I mean, okay, fine. You know what? Let's just get rid of the whole vector thing. We'll just make sure our force and our distance are all going the same direction, right? So force is down. Direction this thing is falling is down. What's the force? Okay, the work is positive. Good job. But like the force is how can we draw the force? What is the mathematical description of the force of gravity on this? It's mg, isn't it? It's just the weight of the ball, right? Okay. So mg. And then for the distance this thing falls, physicists get a little bit annoying. We call this the height. Okay. I believe your book just uses y, which is probably a pretty good symbol to use for this. So I'll write y there, okay, as my, right? But really it's kind of a delta y, isn't it? But sometimes you'll see me just write mgh, okay? Which is the other version of this. As a matter of fact, a lot of the time I'll write mgh because that's the way I initially learned it, and it's always stuck. So H, Y, it's just the vertical height. One of the reasons I don't like putting delta Y into this equation is because we taught you very carefully in chapters 1 through 4 that if the thing is going down, it's negative delta Y, right? Which is true. This is not a displacement. It is simply a distance, okay? So whether it's falling or going up, right? The vertical distance it travels, that's what's going into the gravitational potential energy. The directions don't matter on any of these things because we do work positive or negative. That's all we do, right? As far as directions are concerned. So we're going to call this MGH thing, we're just going to name it the potential energy because it does have units of joules because it's a work, okay? And so with that, we have the sort of the other part of our, this is the first time we're coming up. So we did kinetic energy last time, right? The energy associated with motion. This potential energy is associated with position in the gravitational field. In other words, which of these has more potential energy? Me holding it here or me holding it here? Why did you say that? It's higher, right? There's more distance it can fall. Like this is pretty straightforward stuff, right? So this is where it's going to get a little bit weird, okay? Because it's physics and you know we have to make it harder than it really is. So gravitational potential energy depends on where we are putting zero. When I said, is this one versus this one more or less potential energy, you automatically reference that distance with respect to what? The floor, right? So we need to talk about this because gravitational potential energy can go negative. What do I mean by that? So let's say I've got a full board. Let's use the abomination. Yeah, here we go. All right. So let's say it's about right there. So this is about the level of the tabletops. Those of you in the back are going to have to. Right? That's about a level tabletop. So if I take the ball, I don't know, say like 1 meter above the level of the tabletop. So we'll say that the floor is about 1 meter, right? Okay. So if we put 0 down here on the floor, okay, then I could say that, I don't know, let's say, I'm just totally making up numbers right now, right? Let's say it has 10 joules of potential energy right there, right? If I let go and it falls to the height of the tabletop, and that's the halfway point, how many joules would you say it has? 5. You're doing good. That's exactly right. Okay. So let's look at the change in potential energy versus what the actual potential energy is, depending on where we put 0. So I put 0 at the floor, right? Okay, and I said it was up here. Okay, so what happens if I put 0 instead right here? Now, putting it right at the tabletop. If I drop it and it goes this far, how many joules of potential energy do you think it lost? It didn't lose 10. It only lost 5. If it's 10 here and 5 here, this is identical, same height, right? But it lost 5 joules. But this is 0 now. So what would that make this? This would make this 5. But how would we get 10, right? We need 10 from the ground, right? But we just moved 0. So if this becomes 5, what does that become? Negative 5. Nobody can see that. Okay, right? So what's going on here? This is weird. Picking 0 changes things. So if I have like 10 and I go all the way down and I say the floor is 0, right? Then halfway through I would say is 5. However, I could re-0, right? I could move my 0, which would make this 5 and would make this negative 5, right? I could even put 0 up here, right? So what would the middle place be? Negative 5. What would the bottom be? negative 10. In all three of these cases, though, regardless of where I put 0, because this is starting to get confusing, okay? The change in potential energy makes absolutely no difference. I said that wrong. The change in potential energy is the same. Change in potential energy. What does that look like? Delta potential energy. Okay. Oftentimes it's delta U. Capital U is a symbol that's used for potential energy a lot. So change in potential energy. Let's do. So this is final minus initial, right? So if we take the initial points to all be up here and the final points to all be at the floor, and we're just dropping a ball, right? Then the change in potential, what's the final potential energy for the red one? 0. What's the initial? Plus 10, right? So what's our answer? Negative 10 joules. Okay. For the green, the change in potential energy, what's the final? Negative 5 minus, and what's the initial? Positive 5. What's minus 5 minus 5? Not 0. Negative 5 is negative 10. And then for the blue, what's the final? Negative 10 minus, and what's the initial? 0, still negative 10, right? Do you see how every single one of these changes in potential energy are exactly the same? They all came out negative. Why did the change come out negative? We dropped the ball, right? Why is it a negative change in energy? What would you say about the potential energy of the ball? Where did it go? It got lost and transferred into kinetic energy, right? How much kinetic energy does it have up here where I'm just holding it? See, it's not moving, right? Okay, so it's all potential energy. But as I let go and drop it, right, it loses its potential energy. Whee! Thank you. It loses its potential energy and gains kinetic energy. The change doesn't care where 0 is. The actual values of the energy, whether it's 10 or 5 or negative, whatever, right? Those all depend on where we pick 0. But the overall change will always be the same. And if I'm losing energy, right? I'm losing potential energy, I'll have a negative sign on it. What happens if I throw the ball up? What do you think the change might be? Positive or negative? It's positive, right? As it goes from here to here, it gains gravitational potential energy. Started with lower, ended up higher, regardless of where I put 0. So that tells us that we have a superpower of sorts. The superpower is it doesn't really matter where we pick 0. Like the change in gravitational potential energy will always work out regardless of where we put 0. So does it matter where we put 0? Not for energy, but it does matter for making the problem easier to solve, right? If we can find clever places to put 0, then maybe our math will come out easier, right? Because I'm going to guess of the 3 I just did up there, red, green, or blue, which one feels the best to you? The red one, doesn't it? Putting 0 at the lowest point and then referencing everything positively above it. It gets a little bit, our brain goes a little bit weird when we're like, negative energy, what does that mean? Right? So let's see if we can't develop some rules of thumb here. So here is the process. So I've now taught you basically everything you need to know in chapters 7 and 8. It's now, we've got to put all the pieces together, okay? Kinetic energy is going to come together with potential energy. I misspoke. It's not the gravitational potential energy is not the first one we did. We did springs first. But we're going to follow our problem-solving process, right? We go back to this, right? Whenever people ask me, Mr. Bale, I don't know what to do. Like, I start asking questions like, okay, well, show me your picture. What have you written down, right? I'm asking you to show me your visualization. right? I don't know what to do after that. Okay, let's think about where we want to go. Now, the good news with conservation of energy, problems where we can use conservation of energy, there is one master equation. And a little bit like Newton's second law, we're going to develop this equation. The good news is there are not multiple ones, right? There's one conservation of energy equation, and it doesn't like make more equations the way Newton's second law does, right? Newton's second law all of a sudden turns into 4 equations of 4 unknowns, and you're questioning your life choices. This one, it's one equation. We will put definitions in for these different energies and these different works, and that will challenge our minds. But at least there's only one thing. So once we write out that statement, then we've got to figure out what the heck are we solving for and solve for it mathematically, and then finally come back around and check it. The question, how do I know, Mr. Balogh, how do I know if I can use energy or if I have to use Newton's laws or the kinematic equation, so on and so forth? The answer is actually pretty simple. If you can do it with energy, do it with energy. It's the fastest and simplest way to do physics problems. Physicists, when we encounter something we don't know how to solve or an observation in the universe that we can't explain and we're going to try to explain it, our go-to, well, this is our second one. We go to conservation of energy second. The first thing we go to is simple harmonic motion, which is something you're going to learn in physics 4C. Okay, but assuming I don't know that, conservation of energy all the way. And the way that you know that you can use energy, if you're not being asked or told about time, and you're not being asked about or care about or being told the acceleration, it can probably be done with energy. Acceleration and time. If you're being asked about time or to figure out time, it's probably kinematics. If it's not kinematics, it's power. Okay? And acceleration, what is that all about? It's Newton's second law and or kinematics, right? So energy will tell us nothing about acceleration. It'll tell us nothing about time. That's just not a part of energy. And so if those things don't matter or you don't care to know them, use energy. All right, so it's time to do some examples, okay? And we're going to go back to an example we already know, which is the free fall of a ball, right? So let's, do I have time? Let's just really quickly sketch out what we had to do back in chapter 2, okay? Back in chapter 2, we take a ball, we throw it up in the air. It launches with speed v naught, right? And we want to know, right, what's the maximum height it gets to, right? So what do we know about its speed when it gets up there? We know that its final speed is going to be 0, okay? And so walk me through. If we know the initial speed, we know the final speed, and we know the acceleration, which of the kinematic equations might we decide to use? There were 3 of them. Not the second one. Not the first one. The third one. Yeah, we got there in the end. Why the third one? It doesn't have time, right? Right? And so we could go and we'd have to do some math, right, to solve for that delta y. We could do that, right? We've done that before. So let's compare and contrast that, right, with using this new method. And you're going to be like, Mr. Bale, this is weird. This seems harder. Why can't we just go back and do this with kinematics? I'll show you why in a second. So the way we're going to do this, again, we visualize drawing a picture, labeling 3 very important things. Energy needs snapshots. It needs to know initially what's going on. It needs to know finally what's going on, like where those points are, and then it needs to know where 0 is. You got that? You're home free. So let's do this with conservation of energy. Ball goes up to some maximum height where we know its final speed is 0 and its initial speed is not 0. Its initial speed is whatever we say it is. Okay? All right. So that's what we know. We know gravitational acceleration. It's in free fall, right? Okay. So let's see here. I have to pick an initial and a final point. These are points where either I know something or I want to find something. Down at the bottom, we know something. What can we call that point? That's the initial point. Okay? We'll call that one where we're going to start. And the point at which we're trying to figure something out, up here at the top, that's our final point. So we're 2 out of 3 now. There's the third thing we've got to reference or define, and that's our 0 point. And let me share with you my method. This is not necessarily in books or on the internet. It's just, I've seen a lot of people do this, and it's the one I feel the most comfortable with. I always pick the lowest point in the problem for 0. That isn't always an initial or final point. The lowest point, like that a roller coaster might get to, right? May not be where I'm trying to figure stuff out. But I do like to try to make sure all of my distances are positive above a 0 point. It just feels better in my brain to do that. I can do it any other way. It's just I'm most comfortable and less nervous when I pick the lowest point in a problem. So in this problem, the lowest point happens to be right there, right? So I define those 3 things. Some initial point where something is starting, some final point where something is ending. And at those places, I either need to know something or I need to find something. And then my 0 point, wherever my lowest point in the problem happens to be. All right, so I've got my 3 things. What do I do next? Strategize. Okay, write out the conservation of energy equation. Work other plus energy initial equals energy final. All right, let's tackle work other here. If there is a force that is doing work in the problem and it's not gravity or a spring, you have to put it into work other. This problem does not have any work other in it because what's the only force that's acting on the ball? It's gravity, right? Gravity and springs are exceptions because we have potential energy equations for springs and we have potential energy equations for gravity. They are taken care of in the conservation of energy statement. But if we have any other forces, like say forces on boxes with penguins in them, we would have to put that in work other. Okay? What about air friction? Is air friction gravity? Is it a spring? So where are we going to put it? Wait, we can do air friction now? You betcha. We'll get there. We'll get there. Okay, right? So it's going to start unlocking some additional power for us. But in this problem, there isn't any other work besides springs, with which there's no springs, or gravity. We're going to handle gravity. So we're going to say that's 0. Okay, then we ask ourselves questions. What energy does it have at the initial point? Ask yourself a question. Is it moving? Yes. We threw it up, right? It has initial speed, doesn't it? Okay. So what kind of energy does it have at the initial point? If it's moving, kinetic energy. So it's got kinetic energy initial. And then you ask yourself, does it have potential energy? Are there any springs at the initial point? No. Is there any gravitational potential energy at the initial point? In other words, Is it at 0 or not? At the initial point, it's at 0. So what's the potential energy? 0. This energy initial term right here, you have to consider both kinetic energy and potential energy. I'll write it like this. Potential energy initial, but that's 0, right? Okay, then we do exactly the same process at the final point. At the final point, we ask ourselves, is the object moving? Yes or no in this problem? When it gets to the top of its flight, it stops, doesn't it? So does it have any kinetic energy up there? No. So our kinetic energy final is 0. And does it have any potential energy up there? First of all, are there any springs? No springs. And is it at 0 up there? No. So that means that it has potential energy there, right? So it's got potential energy gravitational. Okay, so what am I left with? I'm left with kinetic energy initial equals potential energy final gravitational. What's the mathematical form for kinetic energy? It's 1/2 mv squared, isn't it? Okay, so 1/2 mv initial squared, and then zeros, and then finally potential energy for gravity. We just did that. What's potential energy for gravity? mgh using Mr. Balogh notation. Okay, I forgot what we were trying to solve for. H. We're trying to find out how high, right, this ball makes it. So now what do I do? This is the do it step, isn't it? Like, we did visualize, we did strategize, now we're doing it. Okay, so let's see. That's going to, m's cancel. Why do the m's cancel? We got, yeah, they're on both sides of the equation and in every term, so we're good to go there. Let's see, that leaves v initial squared over 2g equals the height, right? So 1, 2, 3, 4 lines. I got the height of this ball. By the way, if you come over here and solve this kinematic equation, that becomes negative v naught squared all over 2 ay equals delta y. And that looks pretty much the same, doesn't it? Except in the red, we'd have to remember that ay is negative 9.8, right? And notice in the blue, did we ever ask questions about directions? No. So you might be looking at this going, Mr. Balogh, this seems like you got 2 ways of doing the same thing. Great. I mean, you can check stuff, right? There's a different way to check it. But I don't see why we have to go through this whole rigmarole of initial and final and all that kind of stuff. Well, I do want to show you the power, right, that this kind of thing has. So now we're going to do a problem which, if we tried to do without energy, could cause a brain hemorrhage. Why would that be? Without energy, what does this problem kind of look like? Okay, so let's visualize first. Okay, so we have a tower. We have, right, here's the diver. Okay, how tall is the tower? It's 10 meters tall, something like that, right? And then there's water, and then it says that the diver comes to rest 5 meters below the surface of the water. I want to make it very clear that that diver is not dead. They're just, ooh, that's good. Yeah, no, like they're just, they come down, they've like leveled out, right? They're about to turn and come back up. Okay. Some of you look worried. All right. What do they want to know? They want the force, the average resistance force of the water on the diver. Okay. So without energy, we're asking about forces. So that means what? Newton's second law. Free body diagrams, getting the directions of the forces right, picking a coordinate system, labeling things, possibly finding components. There's no components here, it's just all vertical. Okay, but in order to find that force, I'm going to have to know the acceleration of the diver. And it's the acceleration of the diver where that matters. I'm going to find like the resistance force of the water on them. Only when they hit the water, right? So I've got to do a kinematics problem to find the acceleration in the water so that I can then apply Newton's second law. But in order to do the acceleration problem in the water, I've got to do a kinematics problem above the water, right? I got to find out how fast the diver's going when it strikes the surface of the water. I want to change my major. That's 2 kinematics problems plus a Newton's second law problem, right? No, it's not. Because we have conservation of energy. And one of the things that you need to do is just trust energy. Trust it. It can handle the complexities of all of that in a very, very simple way. If you trust it. And by that I mean trust the method. Trust that energy's got your back. Give it the right things and let it work its magic. As follows. We start with work other plus energy initial equals energy final. I'm kind of doing strategize before visualize, right? But this is the master equation. It dictates everything that you need to set up. We need an initial point. We need a final point, and we need a zero, something that we can reference against. So, where is our initial point? Where do we know something? And where does the object start the motion we want to look at? At the top. So let's put it at the top of the tower, right? That's where we're starting. Where's the final point? Like underneath the water? Or is it at the surface of the water? Trust it. Just trust it. We're going to put the final point down here. Now, 0. I could see how people would look at this problem and say, well, 0 is the water. And if you pick 0 there, it'll work. It'll work just fine. It's just you've got to be really careful if you pick 0 there, because anything under that 0 will be a negative height. Now, I don't know about you. I don't like chasing minus signs around, okay? So I'm going to go with what I feel most comfortable with. And if you're not comfortable with this, that's fine. You don't have to do it my way. You just need to communicate that you know what you're doing. I read lots of physics. I can see it. But I am going to go ahead and pick 0 to be the lowest point in the problem. The lowest point that the object achieves, which again happens to be my final point simultaneously. Okay, so my visualization is more or less done. You basically just need enough of a picture to attach an initial, a final, and a 0 point. Once you have those established, you can start writing out the conservation of energy equation. So we ask ourselves, are there any forces in this problem besides gravity and springs? First of all, are there any springs? No springs. Okay. That example will come later. Do we have gravity in this problem? Is gravity doing something? Yes, but that's going to be gravitational potential energy, isn't it? Are there any other forces on the diver? Well, they don't tell us anything about air friction, right? So we're going to assume, unless we are told like straight out that you have to worry about the air friction, we are going to assume that there's no air friction. But there is another friction. the water force, right? The friction on the diver. And some of you are starting to panic. Oh my gosh, is it static? Is it kinetic? I hated friction. Penguins are my enemy. All I asked was, is there another force? Not what is it, right? But is there another force? Yes, the force of the water on the diver, right? That's not gravity. So, do we have work other? Yes, there is work other here. We'll get to what it is in a second. Okay. Initial energy. 2 questions. You got to ask, you got to think about kinetic energy, and you got to think about potential energy, right? At that initial point, it could be kinetic and it could be potential. What's the question you ask to determine if it has kinetic energy? Is it moving? Is the diver moving as they step off the tower? Technically, yes, but like, what's their speed if they just step off? Their initial speed. They're at max height, aren't they? And at max height, their speed is 0. Okay, so there is no kinetic energy at the top. Is there potential energy? The question you are answering is there 0 here? Is 0 at the top of the tower? No. So there is potential energy there, right? Because the only place there is no potential energy is where 0 is. So there is potential energy here. What it actually is, like the math of it, we'll worry about next step. We're just trying to conceptually work out whether or not there are terms here that we can just say are 0. Okay, at the final point, again, the final could have kinetic energy and it could have potential energy. If I put final on it, that would be better. Okay, so down there at the final point, kinetic energy, what are you going to ask? Is it moving? Yes or no? Down here, is the diver moving? No. And to be clear, the diver's not dead. Some of you are still look worried. Okay? It comes to a stop there, right? Because the diver's going to turn around and come back up to the surface. Okay? So there is no kinetic energy down there. Now, some of you are sitting there kind of, oh, must be good. There's got to be something. No, there doesn't have to be anything. Okay? Because the potential energy at that point is, what's the question you're going to ask about potential energy? Is it at 0? Yes or no? At the final point, is this thing at 0? Yes. So what's the potential energy? 0. There's got to be something. No, there doesn't. Now, don't get 0 happy. Oh, look, work out, there's 0, and it's 0, and it's 0, and it's 0, and 0 equals 0. I can go home now. But realize that there doesn't always have to be something there. And I've given you really concrete questions to ask and answer, right? How do you tell if something has kinetic energy? If it's moving. If it's not moving, it has no kinetic energy. And where is there 0 potential energy? The only place. When it's at 0, right? If the object is not at the 0 that you picked, it's got some kind of potential energy. And if it happens to be below the 0 you picked, it's negative potential energy, right? So those are really concrete questions, and you can go through, right, and really nail down why something is 0. A lot of times, what I'll do is like kinetic energy final, and I drew the 0 through it. I'll just say V final equals 0 as a reminder to myself of why that's 0, right? And why is the potential energy 0? Well, the height is 0 right there, right? Because potential energy is like mgh. Why is kinetic energy? Well, because the initial speed is 0. Like just little notes to myself, right? About why I chose 0 there. And maybe I was wrong. Maybe I assumed something I wasn't supposed to assume. I can go back later and see, oh, I assumed that. Okay, maybe that wasn't right. All right. So we seem to have eliminated most of this energy equation, except for work other and potential energy initial. Should we do potential energy initial first? It's the easier one. What's our potential energy equation, the formula we use for it? It's mgh, right? Okay. And then we have this work other term. What is work? Mathematically. It's a force times a distance, right? Okay. So we have what's the force? What force are we talking about here? What's the force that's not gravity? It's the water, right? Force of the water. Okay. And what's there's a distance that water is acting. It's not the height, right? But you need to stop, and this is the one place vectors kind of sneak in a little bit. What direction is the force of the water on the diver? It's up, isn't it? While this diver's down here, the force of the water is up, right? What direction is the diver going? It's going down, right? So what are we going to put on this work other? When force and direction are opposite each other, it means negative work. So the thing you need to check, the work other term is gonna mess you up more often than anything else. Okay? Look and see if the work is positive or negative. In this case, it's negative because the force applied and the direction the object are going are opposite each other. If, say, a rocket is launching, what direction is the force on the rocket? Which way do rockets go? Up, okay? And the direction they're going is up, right? So that's positive work, right? If a car is accelerating and the engine is working, right? What direction is the force on the car? Forward. And what direction is the car going? Positive. That's positive work, right? But if you slam on the brakes, which way is the car going? Still going forward. But what direction is the force? Backwards. What kind of work is being done now? Negative work, right? So check the direction of your work. I know that sounds weird because work is a scalar, but remember, work can be positive or negative or zero, right? Check it. Make sure that you check and see. Okay, so I've got this, right? What am I solving for? I've totally average resistance force of the water. Is that anywhere in my math right now? Yep, it's right there. Force of the water, right? So I can do math now. Force of the water times D is equal to mgh. What happened there is the mgh went over to the other side, became negative. And since they were both negative, I canceled the negative signs out. So my force of the water is going to be mgh over D. Now I have to put in numbers, right? 70 kilograms, 9.8. What do I put in for H? It's 15. My zero is down 5 meters below the surface of the water, right? So the total height that the diver fell or moved is 15 meters. So I put in 15 meters. And then the D, the distance that the force of the water acted on the diver, is that 15? Is it 10? No, what is it? It's 5. Do I have this? 2,060 newtons. Anybody else get that? Does anybody else care? Don't answer that question. Okay, so in 1, 2, 3, 4, 5.5 lines, we were able to solve a problem that if we had used kinematics and Newton's second law, would have been an absolute nightmare. Maybe 5 pages as opposed to 5 lines, right? Okay? This is the power of conservation of energy. It can be hard to trust that it knows what it's doing. Or maybe I should say, it can be hard to trust that you know what you're doing enough to feed it the correct information. And you'll get practice at that, right? But it does shortcut an awful lot of really, really bad physics if you're willing to let it do that. What happened to all my quizzes? I don't know if there's a quiz or it should be a quiz coming up. Where's my quiz? Object? No, that's chapter 10. You don't want a chapter 10 quiz. Not yet. You don't want a chapter 10 quiz even if it were on time. I guess we don't have any quizzes today. Yay! I don't know if that's a good thing or a bad thing. It's a bad thing. Okay. Haha. Okay. Penguins in boxes, inclined planes in general from chapters 5 and 6. Favorite thing to do ever? No. Absolutely not, right? Okay? Because they're full of badness, right? And all kinds of things that are going on. So let's do the inclined plane with friction. Ooh, right? And see what kind of mischief we can get into here. So inclined planes look like hills. Hills always look like triangles. All right. And then I've got some object. Could be a penguin. Could be a tomato. Could be a Ford Bronco. Could be a cow. Sliding down this slope. Okay. Now that it's sliding down the slope, what do we instantly know? There's friction. What kind of friction is it? It's kinetic. So which way is it pointed? Opposite the motion. Sliding friction, opposite the motion, right? It's going down the hill. I don't want to draw a free body diagram. I don't want to. So let's do energy instead. Okay? And what we're going to do now, can conservation of energy find the acceleration? No. Can it find the tension that's not there? No. What can it do for our inclined plane? Well, do you remember the coefficients of friction? Remember those things, right? And it was always like, where did those come from? Let me show you. The block, the object is going to end up with a V final at the bottom, right? Let's say that we release it with an initial speed of 0 up here. Okay? We know, what do we know? We know that the angle, I'm actually going to give you numbers now, 40 degrees. Ooh, 40-degree angle. Final speed, 28 meters per second. Distance that this thing slid down the hill is 100 meters. Okay? Find the coefficient of friction. All we need to know, how fast did it start? How fast was it going when it got to the bottom? And how far did it travel? If we know those things, we can find the coefficient of friction. And we can do it using conservation of energy. What's conservation of energy look like? Well, it looks like work other plus energy initial equals energy final. What do you want to tackle first? Which term? Initial, final, work other. Initial? I will bring the work other down. Just as a reminder, we got to think about it. Okay, energy initial. It could be kinetic and it could be potential. Is it moving? We didn't make an initial point. Where's the initial point? At the top. Where's the final point? Where it says final. Where's 0? At the bottom. All right. Is it moving at the initial point? No. Got initial speed of 0, right? Sweet. Are there any springs up there? No. Is it at 0 up there? No. So therefore, it has potential energy, right? Okay. Final now. We're going to do work other last. All right. Save the worst for last. Okay. Is it moving at the bottom? Yeah. They tell us the speed, 28 meters per second, didn't they? Okay. So that's not 0. There's no springs in the problem. So is it at 0 for gravitational potential energy? Yes. So that one can go away. All right. So that means I have mgh equals 1/2 mv squared, v final squared, right? H initial. Gotta be careful. And now we're at work other, right? Is there a force in this problem that is not gravity? Yes, friction. Okay, wait a second, Mr. Baylor. What about the normal force? Oh, what about the normal force? Oh, well, good thinking. Because the normal force goes like that, doesn't it? And gravity goes like this, doesn't it? Which means there's a component of gravity like this, right? Okay, well, gravity we take care of where? Potential energy, right? So we don't have to deal with any of its vector components or any of that kind of stuff, okay? But what about this normal force? Doesn't it do work? No. The normal force is exactly perpendicular to the direction this thing is traveling. And when a force and the direction are perpendicular to each other, the amount of work is? Yes. Because the what is 0? Yeah. It's not traveling in the y direction. It's only traveling along the slope, right? So, well, the effective, it's not that the distance is 0. The distance traveled is down the slope and your normal force is perpendicular to it, like by definition. And the dot product between two vectors that are perpendicular to each other is 0. The normal force is doing no work in this problem. So, yay! So what does that leave? Friction, right? What direction does kinetic friction always act? Opposite the direction of motion. So therefore, the work that kinetic friction does is always what? Negative. Negative force of kinetic friction times the distance that this object traveled. Okay. So we figured out the work other. Again, you got to be careful with that work other, right? It can be tricky. It can be positive. It can be negative. You got to identify the force that isn't gravity or the spring. You got to kind of check all the forces in the problem, although things like normal force, like in this problem, are 0. Now, we'll get into other places where normal force gets involved, but for this problem, not so much. Although, I don't see any coefficient yet. Where's my coefficient of friction? We're solving for mu, right? Where is it? Are we having fun yet? No? Yes? No? Yes? Can we swap that friction force for mu times n? You betcha. Mu and d. Und. mgh equals 1/2 mv final. Okay. So now we can solve for mu, but okay. Do we know the normal force? Uh-oh, okay. move on. We'll come back to it. Do we know D? D is a number, right? What is it? 100. Do we know M? No. Do we know what planet we're on? Yes. Do we know the height? The vertical height? No. Do we know a half? Yes. Okay. We don't know the math. Do we know V final? Yes. Okay. So before I can go just Hail Mary on the math, I've got to figure out some more things, don't I? We're looking for mu, so we're not going to mess with that. But we need to find the normal force. We need to find like what the mass is. I didn't give you a mass. And I need to find the height. Which one do you want to tackle first? Height? Okay. Height. The vertical height that this thing starts at. What is it? It's 100 sine 40. How'd you do that? Was that side touching the angle? No. It's a triangle, right? With a hypotenuse of 100. It wasn't touching the side, so it's got to be sine. So my height is 100 sine 40. All right, good. I know height now. What do you want to? Spoiler alert, really the only other thing you have is normal force. So if we're going to find out what the normal force is, what are we going to have to do? Like a really quick Newton's second law. Try not to make it too involved, okay? What do I mean by that? We know the normal force points this way, right? We know gravity points down, and we know that there's a component of gravity opposite the normal force. Do you remember what that component was? Always, like it always showed up. It was mg cosine theta, wasn't it? So as long as there isn't cosine, mg cosine theta, as long as there isn't any other vertical force pushing or pulling on the object, then your normal force is going to be mg cosine theta. So we're going to go ahead and throw that in there. Again, that's a chapter 5 thing. Mu mg cosine theta times d plus mgh equals 1/2 mv final square. Okay, now what do I know? Well, the only thing I don't know is my mass, right? Aha! Why can I get rid of it? Yeah, not just both sides, but it's in every term on both sides of the equation, right? So I can divide every term by m, which effectively means that it would cancel out. So don't need to know what the mass is. Great. Now I solve for mu, right? Oh, I didn't plug in h. Minus mu g cosine theta d plus g times d sine theta. I'll put that back. This is d sine theta over here. Equals v final squared over 2 plus minus. I just multiplied by -1 because I didn't want to deal with minus things. So this is going to be equal to gd sine theta minus v final squared over 2. I'm doing the math really fast. Divide both sides by g cosine theta d. G cosine theta d. That will all cancel. I'm left with mu on this side. All right. And my g cancels there. And my d cancels. And I'm left. What's sine over cosine? Tangent of theta minus, and then there's no hope for this term, v squared over 2gd cosine theta. And if I put in all the numbers that I gave you, my 40-degree angle, 28 meters per second, 9.8, 100, 40, all the different numbers, what I got was 0.32. What are the units of coefficient of friction? Nothing. Coefficient is just a number. Has no units. What have we learned today? Tell me the really important parts of dealing with conservation of energy. Trusting it that it can do it. Set a 0 point. I choose the lowest point. You can choose whatever point you want, but safety is in the lowest point. What else do you need to pick? Besides 0, there's 2 other totally critical things you need to pick. Otherwise, there's no traction. You can't apply it. No. Initial and final. Those are your 3 key things that you've got to get. You got to know where something's starting, know where it's ending, and what the 0 point is. The D's cancel. I got a G and a D. I got a G and a D. Yeah, it's just bad handwriting. So we need our 3 things, right? And then it becomes a chore where work other can come and bite you, right? And then figuring out kinetic and potential energy. That's where you want to fall back on it, right? So late at night when there's no tutors and ChatGPT isn't being any help, and you want to give up and change your major and you don't know where to start, where do you start? Initial, final, 0. Once you've got initial, final, 0, write down conservation of energy. Start asking yourself questions about every term, right? Go back to the YouTube and play this exact 1 minute. It's 9:03 in the morning, right? I pushed play at about 8:01. Okay, so you can go in at 62 minutes and listen to my voice telling you exactly how to do every problem in this chapter. It all starts the same way. Okay? I don't have my pendulum with me. You know what? Let's start this one. And what I want to do by starting it is I want you, working in pairs or threes or whatever, I want you to really discuss this one. You can draw things in a bit, but I want you initially to just kind of turn to each other and start talking. And what you're going to talk about is where are you going to put initial, where are you going to put final, and where are you going to put 0. Go. I did give you a little picture to help you out. All right. How did it go? Like, were you successful, unsuccessful? Was it hard, easy? Like finding zero, finding initial, finding final. Like, how did it go? Smooth, good. Those of you that are not saying anything, can I assume bad? Yeah? Okay. So where is the hang up? Where are you like struggling? Don't be afraid to be wrong. Don't be afraid to admit that you're struggling. Is it zero? Like where to put zero? Yeah? Okay. What's the rule of thumb? Put zero where? The lowest point in the problem, right? That's got some sort of information specified, right? Like, is the cannon sitting on the ground? I don't know, right? But like, I do know like the lowest I know the clown is when the clown is fully loaded into the cannon. So 0, I'll put where that clown is like spring is fully compressed, right? Again, lowest point in the problem. Now, can you pick 0 at, say, the top of the cannon? Yeah, absolutely. That's a valid 0 point. It's just your D is going to end up being negative now, right? Can you put 0 up here at the top? Sure. Then all of your distances are going to be negative, right? It's not wrong to pick zeros at those places. It's just you got to be careful with the numbers, whether they're positive or negative distances, if you do that. Okay? That's why I like to try to get it as low as I can get it, right? So all my measurements, all my distance measurements are as positive as they can be. All right? How'd you do with like initial? Was there any consensus as to where to put the initial point? Where the clown is what? At the spring, and the spring is doing what? Totally compressed. That's where the clown starts. And so if you're feeling lost about like, I'm not sure where to put the initial, just ask yourself, where's the object starting, right? The object in this problem is the clown. I mean, the cannon's involved, but the object doing all the stuff is the clown. And so ask yourself, where does the clown start? It starts loaded in the cannon. So I'm going to try there. If you choose wrong, what's like the worst thing that's going to happen? Red box of doom, right? And then you'll go back and you'll double check calculations and maybe ask yourself, did I choose the wrong initial point? Energy problems tend to go quickly. And they tend to like really start showing if you've set something up wrong pretty quickly, right? And so trust the method and run with it. There's this, I've had this my entire career. There's this concept and idea that if you don't do it perfect the first time, you're a failure. And that is so not true in physics. That might be true in PE or English, right? But like it's not true here, right? You're going to make a lot of mistakes. We want you making mistakes. We want you learning from those mistakes. But we don't want you making mistakes. I mean, ideally, obviously. Do it right the first time, and then we don't have to do it ever again, right? But since when have humans ever done it right the first time? Never, right? Never have we done it right the first time. What we do is we just pick ourselves up, dust ourselves off, and keep going, right? It took a long while for us to figure out how to make fire. Look how fast it took us to get Facebook after that. Like, it just, and that might not be right either. But like, we learn how not to do it 1,000 different ways, 10,000 different ways. And the way you do it is once. Oh boy. Comes as a blow though, doesn't it? I don't know where we get that perfectionist idea, but it is false. It is entirely wrong. And as a society, we need to be better at recognizing when somebody else fails, has empathy for them, right? And encourages rather than, hey, doesn't get us anywhere. All right. So there's the initial. Where's the final? Where's the clown like stop or do something that we know? Right at the top, right? So be looking for those like key points, key frames in a video animation are all like the frame between this one, and then the computer will figure out everything else in between, right? Okay, so initial, final, zero. That's what I asked you to do. Now, in this particular example that I'm not going to have time to finish, and we will continue next time, the M, the K, the H, the D, those things that are in quotes are known values. But I wanted to make sure to do this problem all in symbols, number one, to annoy you. Number two, to show you, right, that there's power in doing it symbolically before you put the numbers in, because you can kind of check things along the way. But those would be all of our known things, right? We are looking for what? We want this, right? We're going to get it from applying this. I can do this in 2 minutes. You want me to do it in 2 minutes? Yeah, just finish it up. Don't leave it for later. Are there any other forces acting on this clown besides a spring or gravity? No, there's no other friction. We're not told anything about the cannon. There's no air friction, nothing. Initial energy. Is the clown moving? No. Is the clown at zero? Yes. Final energy. Is the clown moving? No. Does it have potential energy up there? Yes. Something's missing. The spring. We forgot about the spring on purpose. This is my kinetic energy, right? But the potential energy initial, it's at zero for gravity, but what about the springs? The question for a spring is it compressed? Is it stretched or compressed at that point? The answer is yes, right? So that means there's potential energy there. At the top, does the spring have any potential energy? No, there's no spring up there, right? So what does the potential energy of a spring look like? It's 1/2 kx squared, or in this problem, instead of x, it will be d squared, the distance squared, right? Spring constant, distance squared. And then the potential energy final is mg h plus d. And why did I put in h plus d? I needed that whole thing, right? My distance from zero for the potential energy, yes. Yep, 1/2 kx squared for a spring. The potential energy of a spring is 1/2 kx squared, where x is the compression or stretch. Yep, it's squared, so it doesn't matter if it's positive or negative. What? Kx squared. So maybe did I do it wrong on a different slide? Hooke's law is kx. That's the force. Yeah, this is potential energy. We did a little integral to find it last time. All right, so what am I solving for in this equation? H. So, AMO step, a miracle occurs. Algebra happens. KD squared over 2mg minus d. There will be the height of the clown. Was able to do it in 2 minutes, right? So the new twist on this one was spring potential energy. What's the question you ask about springs? Is it compressed or stretched, right? At the initial, is it compressed or stretched? At the final, is it compressed or stretched? If it's not, if the spring's not there or it's not compressed or stretched at any of those points, then there's no potential energy. Otherwise, it's 1/2 kx squared. Believe it or not, you have everything you need to know to do chapter 8 completely. All I really have are more examples after this, okay? So we'll just keep doing example after example. Let's see, chapter 7 is due Saturday and chapter 8 is due on Wednesday, right? Use chapter 8 techniques for chapter 7. It makes it easier. Just do that. I will not see you tomorrow. Do your homework instead.